All right. Okay. All right, so this right here is just a kind of a picture of how the autoclave sort of works. I just realized we're going to be putting this under a tremendous amount of pressure, and then once again, it causes water to boil at a higher temperature, and then the steam is produced at a much higher temperature. And these literally lock. It's kind of like a pressure cooker or your Instapot. It literally locks. And the autoclave here will not run unless that gasket is completely sealed. And the gasket they replace every, I think almost every 18 months, just because they're so airtight. That if they're not 100% airtight, they will it'll fail. So steam under pressure sterilization autoclave is 15 pounds per square inch, right? 121 degrees Celsius for 10 to 40 minutes. All right. So I think here we do, I want to say 130 degrees for 25 minutes just to be double sure. So it depends on if it's 1 atmospheric pressure, 2 atmospheric pressures, contingent, that will relegate or determine whatever the temperature happens to be. So steam must reach surface of item being sterilized. All right. So that's why you really, I mean, the autoclave is relatively large. You couldn't put a whole person in there, but it's relatively large. You wouldn't want to really autoclave something that big or that dense. The temperature would never reach the inside of the person, or it would take a very, very long time. All right. So it must not be heat or moisture sensitive because we're using heat and moist heat specifically. Mode of action, denature of proteins, destruction of membranes, and the DNA. All right. And we're destroying endospores too, which is the most important aspect. All right. So tintilization is non-pressurized steam. So this we can do, we can use regular steam over these organisms. So we're putting steam over them. We're going to kill all the vegetative cells. Now everything that's a non-spore former is dead, just completely dead. And the spore former is going to produce endospores, right? So we let that sit, and then those endospores will return to vegetative bacteria. Then we steam it again. We wait for those, kill all the vegetative cells, and then whatever's left, vegetative cells are left, we'll make spores. And then we let that cool and let those spores come back to vegetative cells, and we kill all those. So over a period of time, through dilution, we're going to pretty much kill every single vegetative cell, and then as they produce spores and they revegetate, we kill them. All right. So intermittent sterilization for substances that cannot withstand autoclaving, items exposed to free-flowing steam for 30 to 60 minutes, incubate for 23 to 24 hours, and then subject to steam again. Okay, we're waiting for those endospores to regerminate. Then they're vegetative, we kill them again. Repeat the cycle for 3 days to make sure that progeny of endospore producing bacteria are eradicated. Used for some canned foods and laboratory media. It's a disinfectant. Right, so pretty much it's pretty close to sterilization. All right, boiling water, boil at 100 degrees Celsius for 30 minutes to destroy non-spore forming pathogens. It's a form of disinfection. All right, and I was telling the class, I think last semester, back in the day in the 80s when soft contact, late 70s, early 80s, when soft contact lenses first came out, they used to have a little thing that would hold your contact lens case, and then you would plug it in, and it would heat for like half an hour, 40 minutes, and then the red light will go off, and in the morning you could put the contacts back in or whenever they cool. All right, but if you didn't have it with you, or you were someplace where you're camping or didn't have electricity, or your heat disinfection unit didn't work, you could literally boil your contacts in the case. So that's what they used to do. All right. So pasteurization, we've all probably heard of this with food, apple cider, milk. So we're just going to kind of really reduce the microbial load. It's by no means sterile, and there's flashing, and there's different ways they can do this. So heat is applied to kill potential agents of infection and spoilage without destroying the flavor, food flavor, or value to some degree. Right. So 62 to 66 degrees Celsius for 30 minutes is a batch method. 71 degrees Celsius for 15 seconds. That's a flash method. So we're going to increase the temperature few degrees, right? But we're going to do it flash for 15 seconds rather than 30 minutes. Right? Non-sterilization kills non-spore forming pathogens, so anything that's vegetative, and lowers overall microbial count or load, does not kill endospores or many non-pathogenic microbes. And then dry heat. So these are the incinerators we have here in the lab. I don't use them, right? They get super hot, and I'm old school. I like to Bunsen burner, but dry heat using higher temperatures than moist heat, because once again, it's not as penetrating. Incineration flame or electric heating coil ignites and reduces microbes and other substances. So you can stick your loop in there or your needle, and it'll get red hot, and we know that nothing's going to live on that, right? Or we can have dry ovens. They're 150 to 180 degrees Celsius, so that's super hot, and that will literally coagulate proteins too. Using heat for sterilization and disinfection, just showing you like steam under pressure, unpressurized steam, pasteurization, and boiling water. So really the only thing that's going to really sterilize things is specifically for 100% is steam under pressure, the autoclave, for endospores. Tinalization's pretty close, right? We can use it, can be used to disinfect but not sterilize some medical supplies. There's pasteurization in the dry oven and incinerator. Just realize that the dry oven doesn't get red hot, so the object isn't incinerated, but it's close. Right. So that's heat. Now cold doesn't really kill anything per se. Some people will say, yeah, some things just can't live when it's frozen, which is true, but it doesn't kill everything. It's not like an autoclave, right? So microbiostatic slows the growth of microbes, and once again, that's why you put food in the refrigerator. Refrigeration 0 to 15 degrees Celsius, and freezing is anything below 0. Used to preserve food, media, and cultures. Right? So if we have cultures here that we want to, keep for a while, we can put them in the refrigerator, slow down their growth, microbial growth. Desiccation, once again, these are, they pull moisture out of things. Gradual removal of water from cells leads to metabolic inhibition. We dry it out. Not effective microbial control, because many cells retain ability to grow when water is reintroduced. Right? So we can get them super dry, especially like endospores. Slow it right down, add water to it, they'll come right back. All right. Lyophilization, freeze drying, preservation. And this really, a lot of times they'll pull some of the moisture out of something before they freeze it. So, when you freeze something with water, usually it expands. So it kind of destroys the shape of something. And when they freeze, flash freeze, or they do this for food, it keeps the shape and the texture of the food a little better. To do this first. All right, so radiation, there's ionizing radiation, which is what X-rays and all those other gamma radiations is the most penetrating. Deep penetrating power that has sufficient energy to cause electrons to leave their orbit. It breaks the DNA. So literally, we're hitting with ionizing radiation. The electrons literally leave the orbit of the nucleus. They're bounced off. There's the protons and neutrons, bosons. They're not holding those things in orbit any longer. So gamma rays, X-rays, and cathode rays are forms that are used to sterilize medical supplies and food products. And so it's literally radiation source is going in. There's a barrier for us, obviously, and it goes and it hits the cell. It knocks the electrons right off of their orbit, and it's going to start breaking the bonds in the DNA. Right. And they use this for radiation for food, vegetables, and fruits. And you'll see this sign here. A lot of people say, well, I'm not going to eat that. It's been, I'll glow. They used ionizing radiation to kill the fungus or the mold, the bacteria. But it's much safer than consuming like genetically modified food, as far as I'm concerned. Right. But that's just me. All right. So radiation. So see also what we're going to go on and we're going to hit. It's going to break the bonds. All right, of the subunits here. And what it has thymine dimer. It actually causes adenine thymine. Doesn't even bond anymore. It causes thymine dimer here. So when this goes to replicate, it's defective. All right, non-ionizing radiation, little penetrating power, so it must be directly exposed. UV light creates pyrimidine dimers, which interfere with replication. Right there, we see that. Can also create toxic photochemical products. It should be called, spelled that wrong, called free radicals. Right? And there's free radicals in food, and these free radicals are floating around. They start pulling charges off of different organisms and different parts of your cells and different parts of your body. It's not a good idea. UV does not penetrate, has no effect on the cell. Right. And so these have to be, especially if we're talking about UV light, they're going to use it for, like I said, it's very low penetrating. So like water filtration systems where there's just a tiny thin layer of water, can hit it with UV. All right. Oh, there it is right there. Sterilizing air, water, surfaces. All right. And there's from your book, it's just showing you pallets of apples being irradiated with a cobalt-60 machine that emits gamma rays. It's really kind of just killing everything on the surface. Similar to the UV rays on your toothbrush. Okay. Infiltration, I said before, this is for very, very tiny organisms. And this is for things like air or plasma or some kind of liquid we don't want to alter. Physical removal of microbes that passing a gas or liquid through a filter. Used to sterilize heat-sensitive liquids such as plasma and serum, and air in hospital isolation units, industrial clean rooms. And I think one of the students told me that I think it's one of the rooms, the top floor of ECMC is completely sterile. So they filter the air and everything in there. It's a sterile, I think they said, pretty sure, unless they were lying to me. Or maybe someone told them that. It's not true. I don't know. But that's what if you had like a sterile room. That's what they filter the air and everything in that room. Used for water, beer, and milk, and HEPA filters for air. Chemical agents and microbial control. So we'll go over just some basic stuff. Remember, something is aqueous, it's in water. If it's a tincture, it's in alcohol. It depends on, really what it's soluble in. Right, and the delivery system. So disinfectants, antiseptics, sterilants, degermers, and preservatives. And we can, we'll talk about some of these dyes. I think it's Laughlin blue or methylene blue they use on some fungal infections and things like that. And so we just think of dyes as something we use in the lab to stain microbes in the slides, but it also has antimicrobial properties too. So rapid action and low concentration. It's what the thing we want them to do. Or we don't want to have to sit and wait an hour for something to be on, and we don't want to have to use very, very high concentration. So most of the stuff I get here comes in a gallon container, and depending on the use, I can put maybe 2 ounces in a spray bottle, add half a quart of water, and then I have something to clean the counters with in a relatively high concentration. Right. Soluble in water is aqueous, or alcohol is a tincture. These we want broad spectrum and low toxicity. So everything we have here pretty much is broad spectrum. Some of these won't work on like TB and things like that because of the glycolic acid on them, but pretty broad spectrum. It's going to hit most of your bacteria. We want Pseudomonas, and most of your viruses, mold and fungi is going to kill those too. It's got to be penetrating, right? If it's not penetrating into the surface, we're not going to kill the majority of the microbes. Non-corrosive and non-staining. We don't want it staining our hands or our clothes, if at all possible. Affordable and readily available. All right, so there's some things that are super effective. They're super expensive, and not everyone can get them. And even if you had the money, we'd have a problem getting some of them to certain areas. All right. So germicide, incidental means kill. All right, high-level germicidal. So these are the most effective. These are going to kill endospores, maybe sterilants. All right, so they may be strong enough where they can actually kill endospores, and whatever you're cleaning with them is sterile. All right, so devices that are not heat sterilizable and tend to be used in sterile environments like body tissue. So we would want to find something like this would be for, if you're doing a GI camera, endoscope, right? Depending on what end we were going in, we'd want that. Intermediate level kills fungal spores, but not endospores. Kills tuberculin bacillus or tuberculosis and viruses. Used to disinfect devices that come in contact with mucous membranes but are non-invasive. So that's going to be something that's you have your mucous membranes with your immunoglobulin A in them, but this would be something that wouldn't specifically break a barrier. All right. So it could be, I don't want to say like catheter, because no. Yeah, we wouldn't be tearing the mucous membrane. Right? Low level eliminates only vegetative bacteria, vegetative fungal cells, and some viruses. Clean surfaces that touch skin but not mucous membranes. Right? So that's just, you still have your skin barrier, but it's not getting into your mucous membranes. Remember, the mucous membranes are literally outside your body. I mean, you might think of them as inside your body, but they're anything that's exposed to the external environment. So that could be respiratory tract, GI tract, reproductive tract, GI tract, respiratory. Yeah, so these are all things that are exposed to the external environment, and they have a mucous membrane. Okay, so what are some factors that would affect this? All right, so the nature of the material being treated, like I said, if it's plastic, is it glass? Is it wood? Is it, is it like a serving tray? Is it a, countertop in a hospital nightstand or whatever? It depends on degree of contamination. So is it really, really dirty? I mean, if you're cleaning up, I've never done it and I heard it's disgusting, but if you ever had to clean up C. diff or whatever, that, if that can be a heavily degree of contamination, right? Time of exposure. So do we have to leave it sit there for a while, or is it going to be pretty instantaneous? We spray and wipe, or if you're cleaning a floor somewhere, you're gonna mop that up. But just please remember too that Pseudomonas can live on mops. All right, so you want to make sure that mop is bleached or whatever you're using before you clean it, and you got to make sure that you're rinsing that mop off. I've seen, people, I'm not going to say here, but other places where they're mopping something, but they're not rinsing that mop out, or they're not cleaning that mop. So all you're really doing is you're just spreading the bacteria or whatever all over. Right? So you're just spreading it all over like it's one huge petri dish. Right? So the strength and chemical action of the germicide. So how is it? What's its mode of action, and how concentrated is it? So there are some, like chlorine, talking about chlorine bleach. The gas is highly toxic. Solution irritates the skin. And if you don't believe me, go clean your floor with bleach without gloves on, and else it'll start irritating your skin. Right? This can be sporicidal slowly with enough the gas with enough concentration. Iodine, all right, can irritate tissue, toxic if ingested, it's poisonous. Right. Phenolics, all right, so this is poor solubility, and it's expensive, and this is what they phenol is the standard by which they compare everything to. Right. Chlorhexidine, uh, low to intermediate, low tox, fast acting, mild, has residual effects. I've seen this in mouth rinses, dental work. They'll give you like those little star-shaped sponges that you can um, dab your dental, if you have stitches or something in your mouth. Alcohol, hydrogen peroxide, and once again, there's a little asterisk here, but these are sporicidal. So hydrogen peroxide and high enough concentration with enough exposure time can kill spores. And improved stability works well in organic matter. So if you're talking about vomit, blood, feces, whatever it happens to be, quartz is what's in the solutions here in lab, in the beakers, that green solution. So whenever you're using your swabs or whatever, I'm going to put them in the quartz, and then I take them out of there, I put them in the bag, I autoclave them, and then they get incinerated. So soaps, some species react to that, and remember, it's going to go in, it's going to start breaking down that some form of the membrane, causing that cell to lyse. Right? Mercurials, mercury, easily inactivated, highly toxic if ingested, inhaled, or absorbed. All right, silver nitrate. So we'll see this coming up later, but I'm sure everyone has seen The Wizard of Oz, right? So back in the day, they used a lot of these heavy metals in the makeup, especially the Tin Man, the Cowardly Lion. So the skin was absorbing all of these the dyes and the heavy metals in the makeup, and I'm pretty sure both the Tin Man and the Cowardly Lion died of um, toxic liver, because the liver had to detoxify all that. Pretty sure, unless I dreamt that, but I don't think so. Right. Silver nitrate discolors the skin, toxic and irritating, but it is a good bacterial side. Right. And you'll see they usually put this, I think they still do that. They put it in the eyes of infants if they're going through silver nitrate. They use it to flush the eyes, I think, with newborns sometimes. Glutaraldehyde, all right. Um, extremely toxic. Formaldehyde, all right. Um, this is what we formalin, or formaldehyde with a um, very, very effective, and that way that's what they, all the specimens and cadavers and things like that are I don't say pickled. They're submerged in the solution, and it's so sporicidal that nothing is going to grow. There's no viable life in that specimen, right? So nothing theoretically should ever grow. Right? Ethylene oxide gas, sporicidal, very dangerous to eyes, lungs. It's carcinogenic, explosive in pure state. Has good penetration though. Materials must be aerated. So this is what we would use if we had to sterilize something that was relatively sensitive. Dyes are weakly bactericidal and fungicidal. And I said they use this on a lot of skin fungal infections. Right. Right. And the germicidal categories, your halogens, and these are going to be, if you look at the periodic chart, they're going to be all the way to the right. You know, your fluorine, chlorine, bromine, iodine, whatever, how we're going to pronounce it. The phenolics, they said this is what they're going to use. This is the gold standard for disinfection. Chlorhexidine, like I said, they're going to use that on skin, and I think they use it for Staph aureus control in hospitals too. Alcohols, right? Relatively effective. Hydrogen peroxide, I said before, can actually be sporicidal, and it's going to just inundate something with oxygen too, if it's a vegetative cell at all. Aldehydes, so that can change the pH, obviously. Gases, detergents, and soaps are going to be mildly, and this is going to pretty much go from most effective to least effective, more or less. Dyes and acids and alkaline solutions. So chlorine, it's like your chlorine bleach. All right, denatures proteins by disrupting disulfide bonds, denatures enzymes, and suspends all metabolic activity. So at some point in time, that's its mode of action. Right. Intermediate level, so it's pretty effective on most things. Not going to kill endospores. Unstable in sunlight, that's why it comes in those white plastic bottles, so sunlight doesn't inactivate it. Used in water, sewage, wastewater, inanimate objects, and I'm sure you've all tasted chlorine in your drinking water if you're not filtering it. It's used in buffalo in the water sewage plants. Right? Iodine, betadine interferes with disulfur bonds of protein, same as bleach. Milder medical and dental degerming agents, disinfectants, and they have in some ointments. I think we'll see a picture of it. They're going to come up, and I think it's used for like an astringent or to clean skin before certain procedures. All right, it's less susceptible to inactivation by organic matter. Like bleach, is like I said, you can use bleach, but if you're going to use it to clean something, you want to clean up all the inorganic matter. So, not to be gross, but when I first bought my house, there was a problem with the sewer line, and then it kept backing up until I had it all ripped out and replaced. But if it would back up in the basement, I'd have to clean all that up, and then I would bleach it. Right? There's really no point of really pouring bleach on that because it's going to be inactivated by organic matter. So you want to clean all that up, with gloves and whatever, and then bleach the hell out of it. Yeah, here's iodine sponge, prepare skin for surgical incision. Here's water being passed through a chlorination tank. And please realize, I don't know if you guys know, but a lot of times they recycle a lot of the water, drinking water. So if you think about that, it's probably not great because people, they they flush medication and all kinds of things down the toilet. So, hopefully we're using bioremediation and cleaning that up and using, well, luckily in Buffalo we can have lake water. We can clean that up a little bit. All right. So phenols, like I said, this is the gold standard. Carbolic acid is what it really is. Disrupts cell wall and membranes and precipitate proteins. All right. That's how it works. Low to intermediate level, bactericidal, fungicidal, virucidal, but not always reliably sporicidal. All right. So this is your Lysol. Triclosan is the antibacterial additive to soaps. It's only, used to be able to get it over the counter. Now it's only in the US, it's only available by prescription, or you can get it in Canada. And I actually brought, I brought it because we're going to be doing our disinfection and antimicrobial lab hopefully soon. But I brought this, it's called Adicept. You see that? All right, can only get it in Canada. And it says, ingredient, medicinal, it's half in French here, triclosan, 0.5%. All right, so this is what a lot of people use if they have like if they have wicked body odor. There's some people that can take a shower and then an hour later, depending on what's going on, they can smell like they never took a shower. So a lot of times there's a lot of microbial load there, or there's some really resistant bacteria, especially armpits and groin area or whatever, and sometimes feet too. So they have stuff like this. It's detergent and it's got triclosan, so it's going to literally go in and just destroy the cell walls and membranes of whatever that is. So it could be staph, epididymis or staph aureus or something like that, going to kill it. Chlorhexidine is surfactant and protein denatured with broad microbial properties, low to intermediate level. Histamine, and I think we have a little bit of that here in tube, so we can try that on the distant or the diffusing disc to see how that works. Uses skin degerming agents for preoperative scrubs, skin cleaning, and burns. And I think I said before they use this too for dental work. It's an antiseptic cleaner of choice to control Staphylococcus MRSA, methicillin-resistant Staph aureus, Cinebacter outbreaks in healthcare settings. Yeah, here just telling you triclosan, chlorhexidine, some of these properties of it. So when you start working in healthcare, you're gonna see, or if you're see in some of these cleaners or hospitals at the nurse's station or the janitorial staff will have a bunch of these different things. Just kind of be familiar or not of how they clean. Right. Alcohols, all right. Ethyl isopropyl in solutions of 50 to 95%. Yeah, really most effective would be maybe 75, 80%. I just literally got, I think I got 95%. I got one that was like 99%. You can't get 100% alcohol anymore because people used to order it and drink it. Excess surfactant dissolving membrane lipids, that's how it works. Right. Will coagulate proteins of vegetative bacterial cells and fungi only if it's dissolved at least 30% water. So this really would you really want to go and get your 70% alcohol. You can get it, Target, Walmart, or whatever you can get. Sometimes it comes in a spray bottle. I think like dollar stores, they sell it in like 50% solution in spray bottle. Yeah, I used to use it to clean like lenses and clean surfaces, that intermediate level. Hydrogen peroxide produce highly reactive hydroxyl free radicals, OH, right? They damage protein and DNA. That's how they work. And then I wrote in here too, I put in blue, even those microorganisms that can produce catalase, like Staph aureus, if you put a drop of hydrogen peroxide on a Staph aureus, a plate of Staph aureus or a slide of it, it'll start bubbling because Staph aureus will just produce catalase to detoxify the oxygen. Right. Antiseptic at low concentration, strong solutions are sporicidal. And I was talking to a couple of the students here, dental, and yeah, I was saying, people should probably rinse with hydrogen peroxide, right? And actually, and you'll see, you'll feel it foaming, all right? So the bacteria are producing something, and it kills a lot of the bacteria. And I told them before, so the side effect is you're going to whiten your teeth too, right? So there's that. Here's some actions of these. This alcohol gel solution, all right, because you want to pick up something from one room and transfer one patient to another. So this, by the way, this is erroneous. This is not a hydrogen peroxide contact lens case. Hydrogen peroxide, like AOSEPT, they're going to be clear and they have a disc on the bottom, all right, that turns hydrogen peroxide into saline. All right, so that's not, this is, and it will bubble, all right. It's theoretically it's bubbling and killing the bacteria on the contacts, but please realize that's not hydrogen peroxide case. All right, aldehydes like glutaraldehyde is used for heat-sensitive instruments, and I said before, this can kill spores within 3 hours. This is kind of what you're going to use for some of these reusable instruments. And formaldehyde, they don't really use it anywhere. I think we use 37% formalin. It's not as toxic, but once again, you know, formaldehyde was very, very toxic. So we always had people, especially specifically if you were pregnant, right, in lab, we would have you, well, back in the day, you have a mask on. Now we don't use it at all. But even with the formalin, some people are very sensitive to it. We have masks here. Or some people have different masks. I know when I took gross anatomy in graduate school, I had a mask with 2 filters on it because it was, I mean, the cadavers were just soaked in formaldehyde, and you would be breathing it in, and it would be in your skin and in your hair. You couldn't get it out. Even your lab coat and everything just reeked of formaldehyde, right? But nothing was growing on. And some of those cadavers were literally, some of the preserved specimens were maybe 5 or 6 years old. They would spray them down, but nothing was growing on them. Right. And here's ethylene oxide I mentioned earlier. This is a gas. All right. Strong alkali agent reacts with functional groups of DNA. So it's going to just alter the DNA organisms. They won't be able to reproduce. High level, sterilize and disinfect plastics and prepackaged devices and foods. All right. So if we're talking about some plastic dental instruments they use, because they obviously can't heat it, they'll warp, right? And there's just some pictures of it just showing you the difference. Right? Detergents and soaps, the quats, like I said, is the green stuff in the beakers here. X alters the membrane permeability of bacteria and fungus. It's pretty low level. It's better than nothing. It'll kill most of the stuff we have here, like maybe E. coli or Enterobacter or some of these other things are relatively super easy to kill anyway. So just another step we use. Inactive on TB, hepatitis viruses, Pseudomonas, and spores at any concentration. So the only thing it doesn't really affect would be Pseudomonas, and we're only going to be using that once, I think maybe twice, all right, in lab here. But it only works in alkaline environments. And detergents and soaps mechanically remove soil and grease containing microbes. So all you're really doing is you're just reducing the microbial load at that point, right? And soaps make water wetter, I guess. So things tend to remove from the surface, skin or clothes or whatever you're talking about, dishes, whatever it happens to be. All right. And then heavy metals. You'll see this is silver amalgamide, all right, gold foil. You don't want to use this mercury because they did find that although mercury's fillings, there's somebody who would say that it was toxic. It would go mercury and fluoride, by the way, once it gets into the central nervous system, you can't get rid of it. Solutions of silver and mercury kill vegetative cells in low concentrations by inactivating proteins. That's how they work. All right. Methylate, silver nitrate. I said they use that for rinsing the eyes. Silver, copper is being used in laboratory fixtures and doorknobs. Can destroy problematic drug-resistant pathogens such as methicillin-resistant Staph aureus, as Clostridium difficile, C. diff. All right, but these are toxic if ingested, inhaled, or absorbed through the skin. And I mentioned like makeup from Wizard of Oz. for the same reason they're toxic to microbial cells. And there's is it Brazil? Some country, they were near was it a copper mine or whatever? And they had access to a lot of, I think it was copper, and they literally made all the fixtures and the doorknobs and everything copper, and the nosocomial infection rate went way down. Right. Dyes as antimicrobial agents, all right, not the best choice, but they do have some antimicrobial properties. Aniline dyes are very active against gram-positive species of bacteria and various fungus. Sometimes used as antiseptics and wound treatment. Low level, narrow spectrum, so not super interfere with cell wall synthesis. That's why they're so effective on gram positive. They don't really work that well on gram negative because of that outer membrane. Using some ointments, the problem is they kind of stain. All right. And the acids and alkalins, organic acids prevent spore germination and bacterial and fungal growth. All right. So that's good if they prevent spore germination. All right. And then what you can see how we can use them in a lot of preservatives and breads and flours and baked goods, and you can read labels and see this stuff. Right? Sodium hydroxide solution is one of the few substances that reliably destroys prions. And sodium hydroxide, we have it here. I have it in dropper bottles, but I literally have the caution, red skull, and crossbones on it because it's very, very basic. It'll eat right through your skin. Terrible. All right. And then here's the active ingredients in various commercial antimicrobial products. And if you're watching this, please remember in lab, I mentioned that we're going to be doing some antimicrobial and disinfectant on little diffusion discs. It's not going to be actually like Kirky Bauer, but it's going to give you the idea of how these would inhibit growth around these discs depending on the chemical. So start thinking about what you're using at home, and you want to see how effective it is. We're going to be using, I think we'll use E. coli as our gram negative and Staph aureus as our gram positive, or I guess we could use Klebsiella. That is such a huge capsule on it, may not work. So I think we'll use E. coli because that's everywhere. But here, just like Renew, contact one solution, how does it kill the microbes on your contacts? Right. There's a specific chemical agent, and it's like chlorhexidine, right? Wet ones, you know, they're just a basic detergent.